Well, good evening, everyone, and welcome to the Astronomical Society of Edinburgh, to our online talk on the third Friday of each month. It's very nice to have so many people coming online, both in Zoom and on YouTube, and we're delighted to have you along. I'm Nigel Goodman. I'm one of the vice presidents of the society, and I'm standing in for our president, Mark Phillips, this evening. And I'm going to take you through some news and other announcements before we move into our speaker for this evening, Mary McIntyre, who will be telling us about shadows in space and the stories they tell. So before I do that, just draw your attention to the background image that we're showing here. It just shows the standard to which a lot of our astrophotographers are aspiring these days in the society. This is an image of the Elephant Trunk Nebula by Pat Devine, taken from the centre of Edinburgh. So a tremendous image there by Pat, and just indicative of the heights to which our various imagers are ascending. And we also have a number of people in the society who are also observers. So moving on from there, just a couple of reminders for society members. Subscriptions. I'm sorry to mention the horrible word of subscriptions, but they were due as of the 1st of October. So if you haven't renewed your subscription to the society, please do so as quickly as you can. Full membership is a very worthwhile £32 per year. And if you are eligible for a concessionary rate, that is only £16 per annum. And also, because next year is our 100th anniversary, we've been trying to gather some information on what people would like in terms of a celebration of that. So there is a survey online. Please complete that if you haven't already. The details are in the last email that you got from the society. And we really would appreciate your views. Staying in touch with the society has never been easier. We are all over the internet, if you like. Main way, perhaps, is through our website, which is www.astronomyedinburgh.org. I think it is, yes, .org. And on the website, you'll find a huge amount of information about who we are and what we do, how we do it, and all the various ways in which you can get involved with astronomy in this part of the world. You can also keep in touch with us through our YouTube channel. We've got recordings of the vast majority of our talks like these, going back quite a few years now, which are full of information and entertainment, and well worth if you've got a spare hour or two and you want to amuse yourself or learn something. You can do that with our YouTube channel. And you can also, as I mentioned before, you can take a look at some of the amazing images that our astronomers are producing through our Flickr pages. And indeed, you can also keep in touch with the society through the social media of the Twitter and Facebook, Instagram, and Blue Sky. We have quite a full program. We have a talk twice a month, apart from August, which is our holiday month, where we have a little break. But our next talk following this one will be The Search for Life, brackets by someone who's done it, with Richard Shaw, on the 1st of December. And on the 6th of December, we'll be having our imaging and observing group, followed by, on the 15th of December, bringing us up to the end of the year, The Science of the Palomar Observatory, 1936 to the Present, by Stephen Flanders. And then moving into 2024, we're developing quite a nice program at the moment for next year. And that will begin with the Euclid Space Telescope on the 5th of January, Dr. Alex Shaw. Listening to Einstein's Universe, the Dawn, an exciting future of gravitational wave astronomy on the 2nd of February, Professor Martin Hendry. And we will be welcoming back our friend Mary McIntyre on the 16th of February to complete her story of the history of women in astronomy. So, without further ado, let me introduce Mary, and a big thank you to Mary, because we did have another talk lined up for this evening, but that particular speaker had to pull out at the last minute, and Mary stepped into the breach, and she's going to be talking to us this evening about shadows in space and the stories they tell. So I will stop sharing my screen and hand you over to Mary. Thank you.
Thank you. Well, it's so lovely to see you guys again, and I'm really happy that I was free and able to step in to give you what is actually my favorite talk. So I'm going to talk about shadows in space and the stories they tell, as the title suggests. And shadows are everywhere, and by studying them, we can learn such a lot. And the very beginnings of this talk happened when one day I was creating a sketch of Archimedes. Those of you who know me know that I do a lot of astronomy sketching. This was based on a photograph by Craig Howman, and it's a photograph I've used extensively in sketching workshops. I feel like I could draw this crater from memory now, having done it literally 100 times. But what really struck me about this picture is just looking at the shapes of the shadows here. And it got me thinking, like, what is this actually telling us about this crater? And what are the shadows of these little boulders around the crater actually telling us? And it turns out quite a lot. So you can infer quite a lot of information by studying them, studying how they change over time. But you can also take that to the next level and do a little bit of maths. And I know it's Friday night, but there will be a very, very short section where I'm going to just show you how easy it is to actually calculate the height of some of these features. So shadows are everywhere, as I said. So first of all, we're going to start off right here on Earth. And this is a kind of atmospheric optical scene that we probably see frequently here in the UK because we live somewhere that has a lot of clouds. So I'm sure we've all seen these rays. And they are called crepuscular rays because when they were originally named, crepuscular means twilight. So they were referring to rays that were seen after the sun had set, but the rays were still visible. But now the name is just generally used for rays. So you might think, what do sun rays have to do with shadows? And basically the dark bits in between these are usually shadows. So you can see that you see the rays kind of really prominently on days where you have a lot of haze or moisture in the atmosphere. And they are basically just bits of like beams of light that are illuminating that haze, kind of alternating with these kind of shadows that are being cast by clouds. But clouds are not a solid object, although there's a lot of water in them and they weigh a lot, they're very massive, they're not solid. So you end up with little bits of shadow and bits of highlight kind of breaking through. And this picture was taken by my sister Zoe, and she sent it to me saying, I thought you'd like this. And I was like, thank you, this is perfectly demonstrating what's going on with crepuscular rays. So you can even see there's a tiny shadow coming off this little dude here. So when you have lots of clouds, you get these punch holes and beams coming through and interspersed with these cloud shadows. And they are probably the atmospheric optic that's caused me to almost crash my car the most times, because we see them almost daily from the UK, and they're never exactly the same twice, and they're so beautiful. But sometimes those rays are so strong that they actually make it all the way across the zenith and kind of meet at the other side of the sky. So on the sun side of the sky, you'll have noticed in that picture, they kind of extend out in a fan shape. They then go all the way across the zenith and then converge again on the opposite side of the sky. So they start off at the sun, converge at the anti-solar point. And it's kind of weird because these rays are appearing from the anti-solar point, i.e. where there is no sun. And you very often do see sort of just isolated ones with rainbow fragments. I've photographed anti-crepuscular rays and rainbows so many times, but this picture is still my favorite from many, many years ago. And they are just really kind of ethereal to look at. And just seeing these rays coming from an empty patch of sky is really surreal. And on my way home from Barcelona a few years ago, I looked out of the window and nearly fell off my seat when I noticed a full circle set of anti-crepuscular rays coming from an empty spot in the sky. And when the clouds cleared a bit, you can see the anti-solar point, which is just a kind of grey blob, essentially. And if you know anything about atmospheric optics, which is another passion of mine, you will know that at the anti-solar point, you get this kind of backscattering. There's a little bit of, it's called the opposition surge. So where the anti-solar point is, you often get this kind of smudge of brighter stuff. You can see it around your head on a dewy field in the mornings. It's called a Heiligenschein, where you can actually see it around your head. So seeing this from the air was a really special thing. But just your brain gets boggled by how can all of these rays be coming out in a circle from an empty patch of sky. And the reason this happens is basically because the distances are so huge that those parallel rays meet at infinity. And basically, you can see this if you stand on a railway line. Obviously, don't do this if there's a chance there's a train there. But if you look at parallel rail tracks, in the distance, they appear to meet. And obviously, they can't meet, otherwise the train wouldn't go down them for very much further. This picture, which I shamelessly stole off Flickr and haven't been able to find again, so apologies for not crediting the photographer, but nothing demonstrates it better than this square tunnel that's got rails and ducting and all of that stuff. If you look at this point here, everything is fanning out in that circular shape, and that is kind of what's going on with rays. So those rays are actually straight lines. The cloud shadows and the rays are straight lines, and we have photographs of those cloud shadows taken by some of the Apollo astronauts. I think it was Apollo 8, but we've got a more recent one taken from the space station. You can see that they are moving in straight lines, that starting to slightly bend towards the anti-solar point. So that basically tells you something about the distances that those rays are actually traveling in. Now, something else that you might have noticed on the opposite side of the sky from the sun is something called the belt of Venus, and more specifically, the grey band underneath that. That is the shadow of Earth. So as the sun sets on the western side of the sky, you quite often get this more muted coloured pinkish orange band. Sometimes you don't see much colour, other times you see a lot. Again, it depends on moisture, pollution, dust, all of those things. When we've got volcanic dust in the atmosphere, these get very colourful. And basically that you've got that kind of lovely coloured band, and then as the sun goes below the horizon, you start to see this grey band creeping up the sky. And if you time lapse it, you can actually see that getting bigger and bigger and bigger as the sun gets lower. And this is, again, just amazing. It is the shadow of the whole of planet Earth being projected onto that little smudge of color on the other side of the sky. You can see it in the west before sunrise, where it will obviously go in reverse, where you have a dark sky and then the shadow gets lower and lower and lower until the sun pops above the horizon. Then you're just left with the belt of Venus. But it's one of those things, I think sunrises and sunsets, your eye is drawn to where the sun is because that's where the more vivid colors are going on. But just look the other way, and if you do see that grey band, it's the shadow of the Earth, not a bank of cloud, which is what I used to think it was. So definitely keep an eye out for that. Moving on to kind of a bit further out into space, we can't do a talk about shadows in space without mentioning eclipses. Eclipses obviously are all about the shadows. So I'm going to talk about both solar and lunar eclipses. You guys will know this already, but just as a quick reminder, when we have a solar eclipse, we have the moon that is in between the sun and the Earth. Because the moon is so much smaller than Earth, obviously this is not to scale, the sizes aren't to scale, the distances aren't to scale, but the moon is casting a very small shadow onto the surface of the Earth. And if you are underneath that shadow, you see a total eclipse. We are the only planet and moon system within our solar system that has this lucky kind of ratio that the moon is 400 times smaller than the sun, but it's 400 times nearer to us than the sun. So their apparent size on the sky is almost identical. It varies depending where the moon is in its orbit. But I think when we think about solar eclipses, we're so focused on looking at the corona, which is amazingly beautiful, that you forget that you are actually standing under the shadow of the moon, which is why eclipse chasers are sometimes referred to as umbrophiles. And I can see why, having experienced just one total solar eclipse, I can see how people get addicted to it. If you are in the penumbral region of the shadow, there are two parts to the shadow. Obviously, the darker umbra. The penumbral regions, you don't really see very much. And if you're partly in the umbral shadow, you'll get a partial eclipse. But you have to be fully in the shadow in order to see totality. And if the moon is too far away in its orbit, like at apogee, then you get an annular eclipse instead, where you still get the ring around the outside. So with my models, again, using a lamp as my sun source, and these clearly not to scale. The size of the Earth and the moon are sort of to scale, but the distances obviously are not. If we just watch that moving along, you can actually see the shadow has two regions. There's a much darker bit in the middle. And it's amazing that you can actually do that with just two balls and a lamp. You can clearly see that. So as the eclipse takes place, that shadow moves across the surface of the Earth. When you actually look at it as a whole, you can clearly see the moon here kind of moving from the right, slowly covering more and more and more of the sun, until you end up with this bit in the middle where you get the diamond ring, then totality, then another diamond ring. And that all happens so quickly that you blink and it's over. And then you have the moon moving away again. So this was my kind of composite picture done wide field from Glendale State Park in 2017. Amazing experience, would highly recommend if you haven't done a solar eclipse. Now, during totality, we do see these absolutely beautiful streamers of the corona. This is the sun's really far outer atmosphere, and it actually extends out many solar diameters out from the sun, but it's very, very tenuous and therefore not visible unless we have a total eclipse from here on Earth. We do now have telescopes with coronagraphs that block out a lot of the light, but to actually see it like this, you have to have a total solar eclipse. Now, what's interesting about this is the shape of that corona changes depending on how active the sun is. So when we were in Glendale State Park in 2017, you can see that we kind of have two main streamers and a smaller one, which is very similar to this picture here on the left. On the right-hand side, this was taken at solar maximum, where the corona is coming out in many, many different directions. And this is all basically to do with how complex the sun's magnetic field is. Sunspots have magnetic field lines, the differential rotation of the sun at the equator and the poles all kind of serve to cause this massive kind of tangling of the magnetic field lines on the sun. And then occasionally they will just snap back again and you get ejections and all of that stuff. That is very, very complex when the sun is full of sunspots, like when it's more active. But when it's quieter, the magnetic field is a little bit more ordered, and you therefore get those lovely streamers. So that is why the corona can look very different depending on when your eclipse picture was taken. But next time you see a photograph of totality, you'll be able to infer vaguely what kind of activity level the sun was at the time. Actually doing the HDR recombination of a load of manually bracketed shots turns out to be a real headache. So when I got home, having spent 3 days trying to get a decent picture out of it, I just thought, I'm going to draw this because it's easier. And so I did this after the event. There was no time to do this live. But what was amazing is that we could actually see prominences. And I've seen prominences before. We have a H-alpha solar telescope, but to actually see them without a H-alpha telescope really was quite special. And you can see where we've got the prominences, you've got the magnetic field lines like mirrored in the corona. So it's exactly as you would expect, but it was still pretty special to see that. This is actually a satellite video, and what was unusual about this eclipse is just how much landmass it covered. Eclipses are not uncommon, but the Earth is mostly water, and eclipses occur over oceans or the Arctic or Antarctic regions where we can't just go and book a hotel and drive to the line of totality. So to actually get one that covers the whole of the USA like that was really quite unusual. And it's amazing that we got that video from the satellite. Now, one thing that we did was to try to look for this particular phenomenon by putting something white down on the floor, but caught up with having 4 digital SLRs, 2 bridge cameras, and 4 mobile phone cameras, and trying to actually watch the eclipse. We just totally forgot to look at the white thing on the floor. As you approach totality, there is a smaller amount of the sun where the light is actually coming off. So if you look at something white on the ground, you start to see these shimmering bands, and that is just basically atmospheric turbulence being reflected in the light coming from a smaller point source as you get near to totality. And that is called shadow bands. So next time I see an eclipse, I hope we do see shadow bands, but the nearer to totality you get, the more pronounced the shadow bands are. You don't get them every time. It's really just down to, I guess, the bit of the moon, that how many craters there are in that area, what part of the sun is still breaking through, but also on just how much turbulence there is in the atmosphere, and that will vary region to region. So a lot of flies as well. And the insect behavior during an eclipse is also something really fascinating to study. So yeah, all of the solar eclipse is about shadows, even though you forget that sometimes when you're busy looking at the beautiful corona. This is an amazing picture that was taken by Perseverance's left Maz-Cam Z, and this is a Phobos transit. So basically, Phobos is a captured asteroid, we believe. Phobos and Deimos are both captured asteroids, so they're very irregular in shape. But when Mars's moon kind of crosses the surface of the sun, it doesn't produce an eclipse because it's too small. And you can download the raw data of this, which is what I did, and actually turned it into a video. This is basically just a mass cam. It's not even for high-res imaging, but we've got sunspots, we've got Phobos transiting. It's just so amazing. And to actually see a video of this and be able to download the raw data for free to produce this video, amazing. So it's not really a shadow, but it's kind of demonstrating how lucky we are here on Earth that we do have the option of seeing a total eclipse, because you certainly can't get that on Mars. Now, a solar eclipse can only happen at new moon, when the moon basically is facing us. There's no illumination on the lunar near side other than any slight reflected light off the surface of Earth. A lunar eclipse can only happen at a full moon, because the moon is on the opposite side from Earth, from the sun, the opposite side of the Earth. So the Earth is a lot bigger than the moon. So the shadow that is being projected out into space is huge. Like, the moon's shadow on the Earth's surface is minuscule. Earth's shadow is really big. So whereas totality in a solar eclipse lasts anything from a few seconds up to 7 minutes, a total solar eclipse can kind of drag on for several hours. Still beautiful, but they do kind of drag on a bit. If you have the moon just going into the penumbral region, you can see a subtle dimming near the limb. I find that a bit dull personally. I mean, it's still cool, but it's not something that's going to make me go running out in the cold. But even if you get some of the moon going into the umbra, like we had about 3 weeks ago from in the UK, that is really cool, and you can just see a little bit of the moon looks like it's missing. If it goes through the umbral shadow, this darker region, and fully, then you will have a full eclipse of the moon. So they do look kind of different. So it's harder to see the kind of umbra penumbra region on my moon here, but you can just about see it. It's kind of hard to demonstrate using a lamp, but there are definitely kind of darker and lighter regions, so you can sort of see the lighter shadow here and the darker shadow here. So that's basically what's going on during a lunar eclipse. And if you get a partial like this one that I took in 2019, it kind of does still look like there is something obscuring, but obviously the edge of this isn't as like defined as you get during a solar eclipse, because it's a shadow, it's not a solid object. But I actually think that these pictures were better than the pictures I took of the total eclipse. Obviously we don't get totality, and the color down here is purely down to moonrise, but it was a really beautiful event that the press hyped up because it was a thunder moon, as the press do, but it was still a really beautiful thing to observe. But way back in 2015, where I didn't have batteries that could last the entire night, and I ended up making a mess of my all-night stack of this event. You can see the shadow moving across the moon as it passed through Earth's shadow. At totality, the moon suddenly becomes really orange. It can be brown, orange, red. The exact color is really determined by local atmospheric conditions. Then when we get out of the other side, you start seeing the moon emerging from that shadow again. So at a glance, they do look similar. There's a disk obscuring the light from the body that you're studying, but they are caused by very different things. So you can see on these pictures that the edge here is just not that well defined like you get with a solar eclipse. The focus actually slipped on this, and I didn't realize until it was too late and the moon was too dim to fix it. So these are pretty terrible pictures, but the color was amazing. It was absolutely beautiful. And we had a clear night from dusk till dawn and got to see the entire event, and I got to see it visually. So that was pretty amazing. So there's been quite a lot of science done with lunar eclipses. I think like even the ancient Greek astronomers were doing like really amazing work looking at relativity and looking at all sorts of stuff, and also using the moon and the sun and shadows to measure the curvature of the earth, like way back in Aristophanes' time. So there's a lot of stuff that we've learned by studying these, and they are really beautiful. Now, as we approached totality in Glendale State Park, I suddenly became aware of how much darker and crisper our shadows looked. And it's not something that I'd ever really thought about before, but when you see your shadow, it's got a fairly fuzzy edge. But when there is less sunlight breaking through, that is coming more from a point source, you end up with a sharper shadow. So I had to take a picture of Mark and me and my stepdaughter just to show that the shadows did look different. But that's a really good picture to bring us back down to earth for a second, because there's some really interesting stuff I want to talk about with regards to shadows here on earth that we can then use that knowledge of to take out into the solar system. So the sun moves 15 degrees an hour, which means that if you are watching shadows, they also move 15 degrees per hour, which means you can basically make a clock using a piece of cardboard and a straw if you have a protractor, and you can just put those markings on. So you can basically make little videos like that. But as well as moving along like moving sideways or in a circular motion as the sun moves, over time shadows actually get longer as the sun gets lower in the sky. So shadows are at their shortest at local noon, and then as the sun dips again, the shadows will start to elongate. And naturally, the day you decide to film a video showing shadows evolving, it's cloudy for half of it, but that is just a fact of life living in the UK. So there's a great thing that you can do. If you have something of known length, like a 1 meter ruler, you can kind of stick it on the ground, not in, because you want to know the length of it, and just hold that up at 90 degrees. And then you can put markings on, just measure the length of the shadow at time intervals throughout the day. And yet again, whenever I set this up, I end up with loads of clouds. So I got some readings, but not many. But over the day, I ended up with a number of readings here, and each of them were getting longer. So in the end, I was just taking measurements whenever I had a clear spot. I couldn't really stick to my schedule. But if you can stick to a schedule and actually measure it at like proper increments, and around local noon, if you do it at much shorter increments, you will get the time of local noon. So noon is the time when the sun is at its highest point for your location, and that is around noon, which is 12 o'clock in GMT or 1 o'clock in BST. But depending how far east or west you are from the Greenwich Meridian line will change the time of your local noon, and it can vary by about 10-15 minutes depending how far east or west you go. So if you do this experiment, you will be able to find out exactly what time local noon is for you in your location. Now obviously we've had to standardize on this, otherwise buses and trains wouldn't work anymore, but it's really just fun to do this and just figure out what time your local noon actually is. And it's quite surprising how much it can differ depending on where you are. And over time as well, as I said, those shadows get longer. Now, this is a feature that we can use to our advantage and do a little bit of maths. This is really simple maths. I hate maths. I'm rubbish at it, but I really love doing little things like this. So if it doesn't matter what time or date it is, but if we have our shadow at local noon here with our 100 centimeter ruler, I got a measurement of 88 centimeters. So remember, tan of the angle equals opposite divided by adjacent, a little bit of right angle triangle trigonometry. Basically, if we just think of these figures in terms of opposite being how high the thing is, i.e. our 1 meter ruler, and adjacent being the length of the shadow that it's casting, if we know the angle, or if we want to calculate the angle, we just rearrange this because we have tan of the angle equals opposite divided by adjacent, and we have two of those figures already, and tan is just a button that you put on your calculator. So if you do that maths, you end up with a sun angle of 48.7 degrees. If you repeat that later on, the shadow will have elongated and the sun angle will have dipped. Now, this is a really useful piece of maths because at all times within our solar system, we know what the sun angle is at every body. And on the moon, there are apps that you can download that I'm going to talk about a little bit later that can show you exactly what the sun angle is at any time on the lunar surface. And it will tell you that information. So if you then measure a shadow, you can use it to calculate how high something is, because we don't have the luxury of stabbing something into the ground on the moon to then measure what the shadow relationship is. So it means we can do it using photographs. And that is a really, really useful piece of maths, which I'm going to park for now. We're going to come back to it later. But for now, I want to take a look at Archimedes, this crater that I was drawing in the introduction. One of my favorite craters, probably because I've drawn it so many times, but it's kind of in, we've got Sinus Iridum up here, so it's kind of here below Plato. It's a beautiful crater. I just find its morphology fascinating. So this is the picture that Craig Howman took, and this is my drawing of it. Don't look too closely because my drawings are never as accurate as people think they are. But just by looking at this, when we look at a crater from above, you kind of feel that the crater rim is the same height all the way around. But we know from looking at this picture that that just can't be, because if it was the same height, the shadow would be uniform all the way around. And equally, the shadow that's being cast onto the lunar surface this side also really jagged. So we've got indentations and bits that are sticking up. So just by looking at that, without worrying about sun angles or trigonometry, we can infer what the skyline would look like if we stood on the inside of this crater. So without any knowledge about diameter to height ratio, that doesn't matter at this point. If we imagine we're standing here and we're looking at this skyline, not to scale, this is a very crude drawing of what that skyline would look like. And we know it has to look like this, otherwise these shadows wouldn't look like they do. There must be a peak here, otherwise this little thing here wouldn't be sticking out. There's got to be an indentation there, or there wouldn't be a dip there. So we know just from looking at this that that has to be the skyline. And equally, if we turn around and look at the shadows being cast on the other side, we can infer again that the skyline must look a little bit like this. Height to diameter, totally wrong. Doesn't matter. This is just an exercise that you can do with any piece of the lunar landscape. Just next time you look at a photograph or a sketch, just look at the shadows and think, what can I learn by studying them? And this is something I would never have thought about had I not taken up astronomy sketching, because I had taken hundreds of moon pictures. Never once had it crossed my mind to study it and think about what the landscape was going to look like. So even if you draw something once, you have to study it in more detail like that, and it's really good fun. So we can infer that information just by looking at the shadows. Now, we have to be very careful if we're doing this based on one photograph, because as you saw in my short video, when the sun gets lower, shadows get longer. And if you have any protrusions that have a long shadow, it can lead to these long pointed shadows, either on the floor of a crater or alongside a mountain range. And that gives rise to paintings like this. This is some early artwork by Phil Bono, and it makes these mountains look almost like vertical cliffs because the shadows are so long and pointed that you would think that has to be the shape of the object that's causing it. But of course, the shadow changes with sunrise and sunset. So this picture of Ptolemaeus, these two sketches are 2 hours apart. These were mobile phone pictures taken by Dave Galvin from Liverpool Astro. And on the one on the left here, you can see that you've got these long pointed shadows that would make you believe that these bits here must have these huge pointed vertical drops. But if we look at it 2 hours later, we've now got a gentle undulation. So we know that that can't be a big, tall, spiky thing that's creating the shadow. So when you are studying shadows, it's important to do it over a period of time. Unfortunately, crater sunrises and sunsets, you can't do that in a short amount of time. It takes several hours for the sun to rise over a crater. You can see big changes even within an hour, but for a full sunrise, depending on the size of the crater, can be a few hours. Then you've got 2 weeks to wait, because when the sun rises on the moon, it's daytime for 2 weeks. Then the sun will set and you get the crater sunset. But the great thing is that just by looking at the shadows, we can make a model that will demonstrate that quickly. Now, the importance of choosing the right sun angle when you are studying crater sunrises and sunsets can't be overstated. This is the Ptolemaeus trio, one of my favorite trios, one of the biggest craters. And if you look at it when it's near last quarter moon, you've got all of this gorgeous texture. Near the lunar terminator is where you get all that relief, the light and shade that give you those beautiful dark shadows. And you can learn a lot about the landscape looking at it here. But on the right-hand side, when we've got an almost full moon, you can barely see that crater trio. And if it wasn't for Ptolemaeus just being full of lava, you would struggle to even find that if you didn't know what you was looking for. So don't try to do this when there's a full moon, because you're not going to see anything. Full moon is not a good time for studying this stuff. So if you've got a crater of interest, make sure you study it when the shadow terminator is somewhere quite close. And I did, of course, create a pastel sketch of this because it was too beautiful not to. So going back to Archimedes, using a combination of Craig's picture and my sketch, I made this very crude latex model. Diameter to height, totally wrong. We know that. That doesn't matter. What matters is it gives us shadows that are similar to the photograph that I was given. And if I did this again, I'm sure I could get it more accurate. But the beautiful thing about having a model like this is you can use the sun or a torch to demonstrate an entire sunrise and sunset and just show how the shadows change over time. So the shadows go from being those long pointed things into more gentle undulations. When the sun is fully above that crater, all of that relief is wiped out. Then when the sun is setting on the left-hand side, you get the shadows from the other side being cast along that crater. So this is a really useful tool for outreach, because you're not going to get a member of the public to look through a telescope for 2 hours to demonstrate how the shadows are changing. But it's a really good way of just showing. I find people learn better by showing rather than explaining. So any of you can do this. You can go out and make a model based on a photograph and be able to use it for this purpose. Now, I want to talk about another crater. This is the Theophilus trio. And I think when we look at lunar craters, we have a massive disconnect over how big they are. If we superimpose the Theophilus trio onto the UK, it extends from just south of Sunderland all the way down to Cardiff. It's really quite big. And if we look just at Theophilus itself, it would extend from London all the way out into Wiltshire and up like level with Worcester and down to the south coast. So this is a pretty sizable crater, but because it's big, it means that it's a little bit easier to photograph from the Earth, because if the crater's too small, you need a very big telescope to get a high-res picture of it. So these are the good kind of crater to actually do this kind of thing with. Now, remember that we had this formula, tan of the angle is opposite divided by adjacent. We can apply that to these shadows. Basically, the tan of the angle is the tangent of the sun angle, as I said, and then we've got the height of the feature and the shadow that is being cast. Now, if we know the sun angle, which we do, we know the sun angle for anywhere in our solar system at any given time, we can then rearrange that equation, measure this shadow just using a ruler, and then we can apply the maths and actually calculate how high this central peak is. And it is really a very simple piece of maths to do that. So you just rearrange it so you are calculating the height of that feature. So the way that you can do this, you can use the measuring tool in Photoshop, but go for the least technical solution, in my opinion. Just get the crater open on a bit of laptop screen and just make it so you've filled the screen with it so you can get an accurate measurement. Just hold a ruler up to it and measure the diameter of the crater. Now, this relies on you knowing the diameter of the crater in the first place, when that information is available in lunar atlases. If you don't know that, then you need to know what the pixel to kilometer scale is on that camera and telescope setup. So I've only done this for craters because that information is widely available. But we can see that the crater is now shrunk down to 11.5 centimeters. So write that down and then measure the length of the shadows. So I did the central peak, which was just a couple of centimeters, and then the crater wall, which was a little bit longer. So once you have those figures, the first thing you need to do is look up the diameter of the crater, like in real terms, and then you need to just scale that up. So to calculate how long the shadow is in real terms, in kilometers rather than in centimeters on our screen, you just get the real diameter, divide it by what it is on your laptop screen, and then multiply by how long your shadow is. So you can now see that that shadow is 22 kilometers long, because these craters are massive and the shadows are really long. And I think it's mind-blowing when you do that calculation. Even if you don't do the next bit, I think it's awesome to just calculate how long those shadows are in real terms. And of course, the shadows on the moon are really defined because there's no atmosphere there, so you can kind of get a decent measurement of them. So once you've got that, you can then do the crater wall calculation. So you basically just take the diameter of the crater, you divide it by 11.5, multiplied by 3.5, which is the length of the shadow, and you get the length of the shadow there for the crater wall. We now need the sun angle, and there is a really brilliant free tool called the Lunar Terminator Visualization Tool. And I do have a PDF guide on how to do this if anybody wants it, and the download link to this app is there. So what you do is you put the time and date in at the top. So you need to know exactly what time your picture was taken. So you put that in and it will show you where the lunar terminator is at that time. And you can see that it's pretty close there to the Theophilus trio. What you then do is use your mouse pointer, and as you move your mouse pointer around the screen, you'll have a sun angle appearing down here. Now, because this crater is so big, the sun angle is very different at the middle than it is on the crater wall. So you have to be accurate with where you're pointing. But we could see there when I used my mouse pointer that at the central peak where I did my measurement, the sun angle was 3.67 degrees. And when I did it again for the crater wall, it was 4.87. So you can see it's quite a difference in sun angle. So it's important that you're accurate with your mouse when you do this. So now we have the missing piece for our piece of maths. We've got the sun angle. If we know the sun angle, we can then use the shadow length to actually do the calculation. And just whizzing through that, we've got the sun angle, we know the formula, we plug those values in, and we get a height of the central peak of 1.4 kilometers. Sounds crazy, but it's pretty accurate to what the original measurements are. If you do the same thing for the crater wall calculation, obviously we've now got a different shadow length and a different sun angle, but you then get a height of 2.8 kilometers. So how does that match up to the published figures? Turns out quite well. This is a crude method, and I'm going to talk about all the reasons why it's crude and all the assumptions that we're going to make doing this in a second. But I'll take that level of accuracy for measuring something on my laptop screen with a plastic ruler. It's kind of brilliant that that simple piece of maths allows you to do this and to get results that are close enough to have graphs that correspond. So the calculated one is in yellow, in blue is the published figure. So that's pretty close. However, there are some mega simplifications that we're making here. First of all, it's really hard to accurately measure because it can be hard to figure out where the feature and the shadow actually start and end. If you look at this picture of Albategnius, this central peak is casting a shadow, but there's another crater with a craterlet out of its rim here, and that itself is casting a shadow. So we have no idea if this point stops here, here, or down here, or somewhere in the middle of that. So you have to kind of make a few assumptions when you do the measurement. It's really difficult. If you've got a small crater in a low-res picture and you've got slump terraces, really hard to measure it. And also most craters are not perfectly round, so it can get really, really tricky. With mountain ranges, you can try the maths. I've never got it to work because when you look at the length of a mountain range, it doesn't tell you whether it includes the foothills. It doesn't really tell you exactly where the range starts and ends on their measurements that they give you on the atlases. So for that, you would need to know the pixel to kilometer scale of the camera, then just scale that up instead of measuring it on your screen. The other assumption is that the published sizes vary. And the reason for that is because most of the stuff online is people like me who are not that good at maths, who are putting this out there as a school project and sharing their results. So there's a lot of variability, and the methods that people use vary. Crater walls are not uniform. As we saw, that shadow is undulating on all of the big craters. So really taking one measurement is not going to be accurate because there's variation, as we can see from the shadow. The ground is not always level in a crater. If you may have noticed when I showed you the sketches of the sun rising over Ptolemaeus, you could see that the left side of that crater was sloping downhill. If your ground is sloping, it's going to either elongate or foreshorten your shadow. So your shadow measurement is not going to give you an accurate answer. Really crucial, the moon is not flat. The moon is a sphere. And to demonstrate just what a big effect foreshortening can have, this is an 8 centimeter long piece of post-it tape, which I put the divisions on using my ruler, then wrapped it around my biggest Christmas bauble, and then measured how long that tape looks. And it shrinks it down to 5.6 centimeters. Now, obviously, our craters are not the size of the whole moon, but the whole surface of the moon does have curvature. So if it's a really big crater, that curvature can impact your results. So you need to factor that in. Also, if you are looking at craters that are near the limb, they get foreshortened. This is crater J. Herschel, as seen from Earth. This is not a great photo of it, but it's one that I took earlier this year. And it looks like an oval, elongated crater, but the lunar reconnaissance orbiter picture shows that it's perfectly round. So if you measure the diameter of this crater, it's about half the diameter that way than it is that way, when in reality it's round. So you need to allow for that as well. And a crater will get squish side to side and up and down depending where on the moon's surface it is. So if you're going to do this, pick stuff that's in the center because it doesn't get quite as much of the foreshortening effects. Also, measuring is actually difficult. Do you know that you are at the very top of the peak when the peak is a tiny speck on a photograph? Are you measuring your shadow in a straight line from where the sun is casting it? Because if you do it at an angle, you're going to get a longer result than if you do it down the center. So to really kind of firm this up and get it more accurate, what you should be doing is taking pictures all the way along the crater wall at lots of different times at different sun angles. So during an entire crater sunrise and sunset, which means a lot of measuring and a lot of calculating, and then do an average of them. Do I ever do that? No, I don't, because I'm happy to get the results that I get just doing this. And I've genuinely spent my last 2 Christmas holidays doing crater shadow calculations because it's so much fun to do. But just showing you, again, the calculated on the left and the blue on the right is what the published results are. I knew that with Albategnius, I wasn't going to get an accurate answer because I don't know where that shadow finished. So you can see that I calculated longer than it is. So it obviously finishes short of where I put it. The crater wall, not actually too bad, which is a surprise given how much variation there is in shadow length here. I think I was just lucky with where I measured. When I did it with Tycho, again, we've got these complex slump terraces here, but this is a photograph taken by Alessandro Bianconi, and you can see that pretty close there with the central peak. That's the actually most accurate one I've managed to do. A bit more variation on the crater wall as expected because I took one measurement of an entire crater, which has an 86-kilometer diameter. So you can get decent results doing this, and it is just a really simple bit of trigonometry. So I'm going to stop talking about maths now. It's Friday night. We can go back to pretty pictures, and I want to just look at some of the shadow pictures that we've got from around the solar system. And first of all, as we've just been talking about Tycho, Tycho is a crater that is really visible during a full moon. Most of them aren't, but because it's kind of quite small on the lunar disk, it's hard to get a really good high-res picture of it. But luckily, the reconnaissance orbiter, lunar reconnaissance orbiter, has taken this incredible picture. I remember when this was first released and shown about 11 years ago at Astrofest, and there was a collective gasp in the audience. This is my favorite picture still from the whole space industry. I just think it's gorgeous. But it didn't stop there, because he started zooming in and in and in and in. So this is the central peak of Tycho with the sun rising over it. And on the top of Tycho's central peak is a little boulder that's casting its own shadow. How amazing is this? This is stunning resolution, and the whole of the lunar surface has been imaged now in this kind of resolution, and we've got all of these tiny boulders. This is about a 400-foot boulder, but we've got loads of really small ones here, all casting their own shadows. So remember how high res that picture is, because I'm going to come back to it when we talk about something at the very end. But I just want to introduce an important thing to keep in mind when we are studying photographs of bodies taken by probes and we don't have anything there for scale or to kind of give us more information. And first thing to remember is the crater dome illusion. And there's no better way of demonstrating it than with this pesky cheese grater, that in 12 years of having this cheese grater, I have only twice grated my cheese on the right side correctly. I go the wrong side every time because it looks the same. So I'll promise you, one side of this has got the grater sticking up to cut your cheese. The other side is the dome. Sorry, the other side is the crater. So basically, the top one is the domes, and that is the craters. So now I've told you that. Just look at this one. Imagine this is all sticking up towards the screen. That is going to grate your cheese. If I flip that image through 180 degrees, suddenly it becomes craters to my eyes. And this is a really important thing to keep in mind. Sometimes our brain expects a shadow to be in a certain place. So your brain will flip between seeing it as a dome or a crater, even though you haven't really changed anything. So when you are looking at pictures of the lunar surface or other bodies, it's important to keep that in mind. This is Barringer crater. And to me, this top picture looks like a big rocky dome. Bottom one looks like a crater because that's the classic view of it we always see. When you turn it upside down, it just looks like a dome, crater and dome. This picture, one of these things is a lava dome, one is a crater, and there is nothing I can do that makes my brain see anything other than two domes here. So just to put you out of your misery, the left one is a dome. That is actually a crater. It doesn't look like a crater to me. It looks like half of one of Madonna's bras from the 1990s. But if we turn the image through 180 degrees, you can sometimes your brain will then see it differently. They're always domes to me, but it's why it's so important that you don't just rely on what you're seeing in one picture, because it can lead you down a really just a path of incorrectness and complete and utter madness in some cases. Let's have a quick look at Mars. And this picture was launched on the 2nd of February, the first time we've actually got photographs of crepuscular rays on Mars. Phenomenal. I was squealing when I saw this picture. So given that I talked about rays earlier on, I thought it was fitting to include it. All I could think when I saw this picture is, did they look the other way to look for anti-crepusculars? But still amazing work that the rovers are doing. Now, I could do an hour-long talk just on photographs of shadows of rovers on other planets, but what's interesting about this is the opposition surge where the camera is. You can see that brightening around the shadow where the actual camera is, which is awesome. So there's loads and loads of selfie shadows, which are amazing. And we've now got Ingenuity. So this is the photograph of Ingenuity's shadow taken by the camera on Ingenuity during its first flight. Just, I love that we live in a world where this is possible and that we have pictures of it. But we do have orbiters around Mars, and they take these incredible aerial photographs of sand dunes and all of these windswept, gorgeous landscapes. However, that stuff can be misinterpreted. And this picture kind of went really famous when a newspaper labeled it as trees on Mars. What's actually happening here is something has rolled down the dune and exposed darker material underneath. That's how I was told. And that basically is what's going on. But up here, you can kind of see that. Down here, these just look like they're sticking up, especially when the title has planted the idea in your head that these are trees. Of course, they would be a tree that's had a cataclysmic event that's killed all of their canopies, but nonetheless, they do look like something sticking up, especially these ones. They really look like they're protruding. And of course, we know there are no trees on Mars. That's not what they are. This picture taken by Stuart Atkinson, taken by one of the Mars rovers and processed by Stuart Atkinson. It just looks like flat pancakes of sand hovering. It's obviously been processed to enhance the contrast, but just the differing light here, the light and shade, is really messing with my brain when I look at this picture. So we can't really infer anything reliable from this when we think we're seeing floating pancakes of sand. So you need to look at different lighting angles and have something for scale, which is also really important. Going over to Jupiter, or more specifically Europa, when you look at Europa as a whole, it looks fairly smooth apart from some of these larger scarps. And we did get a new flyby of Europa by Juno. This is Connemara Chaos, and it's an area that has been studied extensively by probes. And again, you can see this is a higher res picture from Juno, where you can really see all of the scarps when you've got that relief with the, like, near where the Terminator is. But Connemara Chaos has been kind of studied quite extensively by the Galileo probe. And when you look up close, you've got all of these cliffs and these kind of weird channels. And basically what we think has caused this chaotic terrain is multiple freeze-thaw cycles and slush coming up through cracks and refreezing, and then melting again, and slush coming up through some other cracks and refreezing. And it's an incredibly chaotic and complex landscape. Now, if you obviously can't see this sort of detail from Earth anyway, but we only really get to see stuff with a high lighting angle when a planet's at opposition. So we just don't have the luxury of seeing this kind of shadowy detail unless you can look at it under different lighting angles, which is why we need to send probes everywhere. And the chaos terrain was studied under lots of different lighting angles during the period from 1995 to 2003. And they showed these ridges and icebergs were really big. Some of the icebergs are around about 5 kilometers across, and some of them are like 100 meters tall. So they're pretty sizable chunks of ice. And this is information we just wouldn't have known had we not been able to study it under a lower sun angle that allows us to see the terrain and the shadows. Moving over to Saturn, the Cassini probe, honestly, I could just lose myself in Cassini images for the rest of my life. But being able again to look at Saturn under these different lighting conditions that we just can't see from here on Earth, having the shadow of the planet just completely obliterating a chunk of the rings. But what's also interesting is this bit here, the rings themselves very thin, the shadow of them being cast onto the illuminated surface is giving this kind of impression of a belt pulling. It's just an optical illusion. It looks like my jeans did after the second lockdown, after all the biscuits, but it kind of gives you that, it just messes with your head when you see light and shade in this way. And being able to look at the way that the shadow with the rings being projected onto a curved surface can give you these really interesting shapes and forms that we just can't see from Earth. And seeing the rings edge on while their shadow is being cast down here, just gorgeous. And this picture really makes my brain hurt. Every time I think I've got my head around what I'm looking at, it just messes up again. But basically, this is the rings. So we're looking at the rings from kind of the side of Saturn, but underneath we've got the shadow of the rings from where the sun is casting a shadow to the left, and slightly up. So you've got the shadow of the rings on the curved surface below, but the rings themselves in a slightly different orientation. And it's just crazy. It's like, how can stuff form diagonal crisscrosses? It's just gorgeous. And these images are so scientifically valuable. But more scientifically valuable was the fact that being able to study Saturn and rings in particular under a low lighting angle told us some stuff that we didn't know. So if you look at this bit here, we've got a shadow. And remember, where we've got a shadow and we know the sun angle, we can do that bit of maths again. So by doing this and looking at these shadows along different parts of the rings, it completely transformed our knowledge, because we always thought Saturn's rings were about the height of a two-story house. In reality, there are chunks in the ring that are taller than the Rocky Mountains. We would not have ever known that had probes not gone there, and we do this trigonometry with the shadows. And I think that is mind-blowing for that simple piece of maths. And the photographs are amazing, like the edges of some of the ring structures with these long, jagged structures. Obviously it's a low sun angle, so they're not really as high as these shadows infer, but they're just so beautiful. Then you've got the little shepherd moons in the gaps in these wave edges here as well. So this is Daphnis, and we've got a lovely shadow of Daphnis and all of these edges casting shadows. Then we've got this long shadow of Mimas, another moon of Saturn, again with all of the wave edge jagged shadows here. It's just gorgeous. It goes on and on and on. I could honestly talk for 2 hours about Cassini. But I want to move on and talk about Comet 67P Churyumov-Gerasimenko. This is a very mediocre picture of said comet that Mark and I took from our observatory in Oxfordshire. Not a particularly bright comet, so this was a challenge. But of course, we had the Rosetta mission actually visiting this comet, and as well as getting these up close pictures of the outgassing, it is full of shadows and craters and cliffs, and again, no atmosphere and a lovely bright sun angle giving you all of that structure and definition. I don't think I was expecting this. I didn't expect to see pictures like this when we had that mission. They are incredible. These lovely shadows being cast by these big scarps and cliffs, and just stunning, absolutely stunning. Asteroid Ryugu, we had the Hayabusa 2 mission go there, and this is a shadow of the spacecraft with the opposition surge around it again, that bright spot. And we have all of these cliffs on this asteroid as well. The video from this is insane, because when it crashes down to collect the sample, it basically just disperses a huge rubble pile, and you can see the shadow of all of that rubble being kicked up as well in the video. So all over the solar system, wherever we've sent probes, we see shadows like this, and it's just gorgeous. Now I just want to finish off by talking another fun little thing that we have to also keep in mind when we study space probe pictures, and that is something called pareidolia. And the human brain loves to assign an actual thing to something that is random. So this is a perfect example of a picture taken by Peter Chappell in Iceland in a geyser, a blast of steam from the geyser. He didn't even notice until he got home that this is basically the side profile of a face. And I don't think other animals actually have this ability, but it's something that humans have evolved fight or flight response. It's better to actually see a tiger than to think you've seen one and not run away in time. So we are terrible for actually seeing things that aren't there. And we really do often assign human characteristics to stuff like that. So if we look at the moon, there we go, my slides weren't changing. So we have a picture of a full moon. And when I was a child, everyone was always talking about the man in the moon. I could never see it myself, but I was terrified of the man in the moon, so I didn't know what he was. But the place where people see the face, one of the faces is kind of, this is obviously a piece of artwork, but it shows you which Maria are involved in that kind of formation of a face on the surface of the moon. But we also have the face of Albategnius. So that picture I showed you earlier where I did my shadow calculations, about 2 hours after the lunar X is prevalent, which is here, 2 hours earlier, you would have the X visible on the shadow side and nothing else. This shadow here forms the side profile of a face. So there's an eye there, there's a nose there, and a mouth. And it's only there for a short time, but it's always a couple of hours after the lunar X. The times of all of these phenomena are always on my blog every year, by the way. I love clair obscure effects, which is what these are. So if you want to know the lunar X and the V up here and the face of Albategnius and also the eyes of Clavius, the timings for the whole year get put on my blog every January. And this picture taken by Mel Gigg, soon as I saw this, I have never seen this effect before myself. There's a peak here that's just catching sunlight. And obviously we've got the side profile of a face and all of this hair. First thing I thought when I saw that is Barry Manilow. Now, no shade to Barry. I grew up listening to Barry Manilow. I love him. But that's just Barry Manilow on the moon to me. But somebody else would see it slightly differently. We have the eyes of Clavius, as I just mentioned. The two craterlets hit the light first during crater sunrise, and you then end up with these two bright eyes looking out from the shadowy void. So I didn't even realize I'd taken this until a few years later when I became aware of what that even was. We do it with galaxies. This is the great galactic face, and it's a seriously creepy face. Anywhere where there's two of something, we see eyes, and it's the same with Copeland's eyes, another pair of galaxies. That's what they're called on the catalogue. So humans really love to put faces on stuff that really has nothing to do with faces. Now, there are great scientific journals out there like the Daily Express that like to tell us that there's a secret conspiracy and there are astronauts working on Mars without our knowledge. There is nothing in this picture for scale. You have no idea how big this shadow is. So while it vaguely has human proportions, and maybe that's a leg and a boot and a it's basically something that has vaguely similar proportions to a human body, but it's just a random shadow of a Mars rover. This one also looks a little bit more convincing because of its position. It looks like an arm and a breathing pack. But again, nothing for scale. This is actually the robotic arm that cast this. So when it was slightly turned at an angle and you had the sun in the right position, it just kind of vaguely resembled human proportions in a spacesuit. So there's no conspiracy here. I hope we do get people on Mars, but we don't yet. Now, I'm sure a lot of you will remember the fuss around the face on Mars during the Viking mission. This guy up here does look like a kind of creepy mask. People have taken that and really run with it, and this photograph is just crazy. So we've got a fortress and slave quarters and an ancient city and a pyramid. And Bert, where did Bert come from? Like, it's just honestly bonkers to me. So obviously this has been digitally enhanced in some way, but why would we want Bert or Tin Man on Mars? It just doesn't make any sense. So this is the famous face on Mars. There were so many documentaries on Discovery about this during the 90s that I remember watching. So I wanted to kind of put this, like, we know how big the Sphinx is. We've all seen people standing next to it. I wanted to put the number of Sphinxes along the side of this to give you some scale. I can't, because it's 150 Sphinxes long. That is a lot of chipping away to make a human face. Like, the actual lava butt looks like this when you get a high res picture of it done by the Global Surveyor in 2001, as compared to the face on Mars, which was a super low resolution thing. Why would somebody want to go out with a chisel on a lump of rock that is 3.5 kilometers long and chisel a face? Who knows? Like, why would we? The woman on Mars is another one that gets a lot of traction. If you're struggling to find her, I'll help you. She is there. She's basically a smudgy few pixels, vaguely human proportions, again, very ethereal. But woman, I mean, come on, there's nothing for scale. But I found the original, and that is the wheel of a Mars rover. She is probably 6 or 7 centimeters tall. This is the thing, they always crop out the stuff that gives you any sort of scale. That is basically probably a bit of dust on the camera sensor. You know, it's just nothing. And this is a mermaid. Look how small that is. Like, the tiny mermaid on one of the driest places in the solar system. It's basically about 200 blurry pixels. Like, what's she doing? Just chilling, waiting for the tide to come in. And we also have an iguana on Mars. To be fair, that does look like an iguana, but is this iguana 6 centimeters or 6 kilometers? We don't know, because that information has always disappeared. There's no meter ruler next to it, or there's nothing for scale. So we have absolutely no idea how big these things are. My favorite, within less than a week of Perseverance beaming back pictures, we found Les Dennis on Mars. Luckily, because there'd only been like a week's worth of pictures, I was able to dig out the original, because obviously the one that was in the Sunday Sport, which is where we all turn to for our scientific journal knowledge, obviously, I found it, the original, because this has clearly been photoshopped. And I was just like, genuinely, what were they drinking? Because they are seeing Les Dennis's face on that. It's genuinely so hilarious. But basically, people, all the forums are full of people that look for the latest releases from NASA and go through and find this stuff. I mean, yeah, great if you've got the time. I do not. But it also leads to lots of architecture conspiracy theories. And I get basically messages from people about this all the time on my Flickr page. There's no way that these slump terraces can be natural. If you've ever built a sandcastle with a moat and watched the tide coming, you can see it's a totally natural process after an impact, when all the surrounding stuff has been loosened and starting to fall down. So no, they're not quarries. This is a totally natural thing. Whenever you try to engage with people that believe these architecture conspiracies, these are the pictures that they always pull out. They're like really low res frames. I mean, again, the detail that people have gone into thinking here, this rectilinear arrangement and geometric squares, and this is Archaeology Row. And there's a castle that's kind of floating in the sky and a strangely obscured horizon. It's just because it's a low res picture. A castle, honestly, you know what, there's no point even trying. And this is apparently hard evidence of a city, an ancient city. Remember this picture I showed you earlier? This is the resolution we now have of the entire lunar surface. These aren't the pictures people bring out to show you slave quarters and faces, because we can see it for what it actually is. And I'm so grateful that we do live in a time where we have these pictures. And of course, this is one I've wanted to draw for years. And last year I finally created my own pastel version of that picture. So I will finish there. If anyone has any questions, feel free to pop them in the chat or unmute, etc. Thank you.
Well, thank you very much, Mary. That was absolutely fascinating. And could I ask people to unmute and thank Mary in the usual fashion? And now we'll see if there's any questions. First of all, I think on Zoom for Mary.
Can we see if anybody's got any questions for Mary?
I hope you're all planning to go and do some maths this weekend.
No, no, but we could ask you what's your favorite distortion of a shadow?
It's got to be Barry Manilow. I mean,
Right.
that's going to take some beating. I do really love the Lunar X and V. I don't know why I'm so I really feel very attached to the Lunar X and V, even though there's not really that much in terms of distortion. It is just literally the rims of some craters forming an X. But I just feel really happy when I photograph it. And it's not a face. I'm a bit over everything being faces. So, but yeah, there's so many. They're all just so interesting and so beautiful. Like, there's a massive list of clair obscure effects to look for now, and there's loads of informal ones as well. I think there's a list on Wikipedia to look for them. And a lot of them are only visible for a really short amount of time once a month. And of course, we don't get the same phase every month, so you only get a few times a year to look for them. So I do quite enjoy the challenge of that.
Very good.
Is that anything else, Peter?
Nothing else at the moment?
Nothing else. Will, anything from YouTube?
Yes, there is. There's been a great response. Loads of people watching, Mary, and everybody's thanking you at present. We've actually got one question from Martin C. This is just before you really went into the depth of your shadow stuff when you were talking about your solar eclipses and stuff. And Martin C asks, hi, do we know the strength of the magnetic field of the sun flares compared to the Earth's magnetic field?
I'm sure that information is known. There's quite a lot of research being done on the magnetic fields and measuring those things, particularly with regards to sunspots and things that have reverse polarity and stuff. From the top of my head, I don't know what the figures are, but they are pretty strong. The magnetic fields are quite strong, and I guess because they're getting chewed up, you get that like real kick off of material. I don't know how that compares to Earth's magnetic field, because ours is fairly stable. So it's but it is interesting when you do look at highly polarized sunspots, because they follow exactly the same pattern that iron filings in a bar magnet do, and you can actually see that in the corona as well, and in the chromosphere. So it is a really interesting, I know there's a lot of research going on that, and I know the probes are looking at that around the sun at the moment. So, and I don't know how they did it, but I remember when I was doing my Open University stuff, there's a lot of magnetometer data from the sun, but I have no idea how they measured it, but we do know a lot about it. So yeah, I honestly don't know the exact figure compared to Earth. I'm sorry.
Yeah, I suppose it's quite a difficult thing, and as you say, all the probes in space are the ones which will really sort that out. I would just say, from personal experience from my side, I remember about 2005, we had some very heavy sun interference affecting the Earth, and I was away offshore and was measuring the dip angle about 3 kilometers. 4 kilometers under the ground, the Earth's magnetic dip angle, and actually we saw a variation of about half of the degree, and so the sun actually caused a variation of half a degree of the localized dip angle during high solar activity, which was quite amazing to see. Actually caused lots of problems for directional drilling, but it was just, as an offside note, that's the biggest sort of change I've seen from sort of underground measurements. So it's been quite interesting.
We've had a couple of, like, if you remember the Carrington class event from like way back in history, if we had something of that magnitude now, it would cost something like $4 billion in the US alone, which is why there's so much research done on solar activity, so that we can be prepared for that and looking after the power grid systems and all of that stuff. We have had 2 lucky escapes from that, because we've had 2 absolutely immense explosions on the far side of the sun, which, had they been Earth directed, would have probably been Carrington class. And while I'd love to see the aurora associated with that, I rely so heavily on GPS to get me from anywhere more than 2 miles from home, and that gets impacted by solar activity, and so do satellites. There was a whole batch of Starlinks that were lost because of a geomagnetic storm when they hadn't quite reached their orbit yet, and that whole batch of satellites deorbited. So the effect of solar activity is very, very important research for, especially today. We have so much more technology than we had last time there was a big event. In the 80s, I think Canada lost their whole, was it the whole of Canada? Certainly a huge chunk of Canada lost their entire power because of a solar storm. So they definitely have things in place to protect the power grids now, because that is a major thing. You know, we rely so much on this technology, and the damage that could be done if you're not ready for it. But yeah, it's really hard to predict still. We can't predict exactly when there's going to be a flare or an eruption, or exactly how the aurora will get affected. So it's ongoing research. It's a fascinating field.
Excellent. Thank you. That's all
off
from
topic. Sorry.
That's all from YouTube. And must say, I'll be definitely looking at shadows in different lights now. Thank you.
Well, thank you again, Mary. It just goes to show that you can always count on a Lancashire lass to help you out when you're in a spot of bother. And I, for one, will be following your blog from now on. And I can't wait to your talk to us again in February of next year. So if we'd just like to close the meeting by saying thank you again to Mary in the usual way.
Thank you. If any of you do want the PDF step-by-step of how to do the shadow calcs, just drop me an email. I'll send it over.
Fantastic. Well, if anybody wants to do that, just contact myself and we'll be, or Sarah, and we'll be able to pass that on to Mary. Thank you very much, everybody, and good evening, and we will see you again in the early part of December.